So good evening everyone. In our last class we have been talking about the DFT and we have discussed why DFT is important and when we sample the signal even in the what you call frequency domain, we have seen that the signal becomes periodic in the time domain also. Okay, so in gist, what we discussed is that sampling in the time domain create periodicity in the frequency domain and vice versa. Okay, then we talked about this these two equations where the first one is the DFT equation. The first one is the DFT equation, that means it is the forward transform equation, and the second one is the inverse DFT, that is the inverse transform equation. So the first one helps us to get the signal into the frequency domain, and the second one, it helps us to get the time domain signal from the frequency domain signals. Okay, so we also talked about this total factor. Okay, so which is given by Wn equals to e to the power minus j 2 pi by capital N. Okay, what is this capital N? This capital is nothing but the length of the signal. It is nothing but the length of the signal. Okay, now over here if you see that we have got W to the power kn, and in the subscript we are having n. So what does this mean? This means that suppose we are having nk like this, so we'll be having this multiplied by nk. Okay, this multiplied by nk. So what are these things? If you see this thing as a whole, Wkn equals to e to the power minus j 2nk divided by capital N. Okay, now here Wkn, it is the total factor of the kth term in the DFT of a sequence of length n. Okay, and j is the imaginary unit j, which is equal to under root of -1. K is the index of the frequency component being calculated. So this k term, this n and k, these are two independent terms which are associated with the frequency components that we want to calculate, and the multiplication of this one it gives us a real number, say for example 0, 1, 2 and up to n. Okay, so capital N, as I already told you, it is given by the length of the signal, or you can say n is the total number of points in the DFT. Suppose it is a 4-point DFT, then you, for a signal which is having a length of 4, you can analyze that signal using the 4-point DFT. Okay, so over there you have to have a total factor matrix which is having a dimension of n by n. Okay, n cross n. Okay, so let us look into the sequence. So let the sequences be represented as vector x of n, which is the time domain signal. Okay, so it is having a length of capital N by 1, that means 1 column. So what happens is that usually you will be given xn equals to, in this format, say 1, 3, 5, 4 and so on, it depends. So it will be in the row wise format. However, during the calculation you have to put the signal in the column wise format. Okay, then comes our total factor matrix. So when we have this total factor matrix, so what happens, we were having two variables, nk, small n and small k. So what are these? So let us take n and k, n for the rows and k for the columns. Okay, so we'll be having 0, 1, 2, 3 and up to capital N. Similarly, the k values would be 1, 0, 1, 2, 3 up to capital N. Now, how this nk value is being calculated? Nk is nothing but multiplication. Nk is nothing but it is a multiplication of n and k. So 0 multiplied by 0, we are having 0. Then 0 multiplied by 1, 0. Again 0 multiplied by 2, 0. 0 multiplied by 3, 0, and so on. Okay. So anything multiply to the power of 0, they are 1. Similarly, in the first column also, if you see everything in the superscript, it is 0. Okay. So the first row and the first column will always be 1, whatever total factor you want to find out. Whatever total factor means, if you want to find out the 2-point total factor matrix, or 4-point total factor matrix, or 6-point total factor matrix, or 8-point total factor matrix, and so on. Okay. So for the purpose of class, we will be basically restricted up to 8-point total factor matrix. That means you should be able to calculate 2-point, 4-point, 6-point, and 8-point total factor matrix. So if you see, in all the cases, if you see, I am talking about a DFT method where your values, they are changing in the ratio of 2 to the power n, where n can vary from 1 to infinity, 1, 2, and so on. So 2 to the power 1, 2, so 2-point DFT, 2 to the power 2, 4, 4-point DFT, okay, 2 to the power 3, 8-point DFT, and so on. And in between, we are also having this multiplication of 2, basically. Okay, so 2 to the power n plus any point in DFT which is multiplied by 2. Okay, say for example 6. Okay, 6, then 12 or 10. So these are all having multiplicity of this 2. This 2 to the power n DFT, when we implement it using the FFT, then these are only the FFT methods which can be implemented by the DFT, that can be implemented by the FFT. Okay, so that means 2, 4, 8, again 16, and so on, right? So next is the DFT. So once you have calculated over here this total factor matrix, another important thing, if you look over here, the next column, it would be 1, 1 multiplied by 1, 1, 1 multiplied by 2, 2, 3, and so on. Similarly, 1 multiplied by 2, 2, 1 multiplied by 3, and so on. Then 2 multiplied by 2, 4. So in this way, you have to calculate the whole DFT matrix. I hope you people have understood what I mean to say, how to calculate the total factor matrix. Okay. Now these points, whatever we are talking over here, if you look into the total factor matrix over here, so it is basically in a complex plane. Okay, and if you want to find out the modulus of the total factor, modulus of this one, what it will be? Modulus of this one, modulus of Wn. So you know it is equals to e to the power minus j 2 pi by n. So if you have to find out this modulus of this one, so what we can write it down? We can write it down as e to the power minus j theta. So how you can break it down? Modulus cos theta minus of sin theta, j sin theta, right? Then again उसका modulus under root of cos square theta plus sin square theta, right, which is equal to 1. Okay, so we are working. So whose this modulus is 1? Any circle, right? Any circle, if you are having a circle, its modulus will always be 1. Okay, having a radius, any circle having a radius of 1, it will be having a modulus of 1, right? So in the complex plane, since we are having this j component, that means in a complex plane somewhere there is a circle and we are interested in that circle. Okay, so we'll be coming to that in a few moments of time. So let's see the next point. In the next point, what you have, capital X of n, it is equal to total factor multiplied by x of n, small xn. So just you have to multiply xn with the total factor and you'll be getting the DFT, right? Which one? W to the power? This one? Are you talking? In the matrix? Huh? So n and this one? Yeah, correct. Because this type of filtering, it has been designed only for this to handle even values. Okay. So capital of xn, it is equal to total factor into x of n. Okay, then we have, if you want to go to the this small xn, which is the time domain signal, you just look into here. It is 1 by capital N, that means 1 by length of the signal, w conjugate n multiplied by x of n. Okay, so conjugate means, so if you are having a plus jb, its conjugate would be a minus jb, and vice versa. If you are given with a minus jb, its conjugate would be a plus jb. So you have, instead of this total factor, in the inverse discrete Fourier transform, in the inverse transform, you have to use this conjugate, total factor conjugate. Okay, so whatever values you will be getting here, so you have to convert it into the conjugate and then you have to use it for the IDFT. So that multiplied by frequency domain components, okay, what you will be getting multiplied by 1 by n. So that would give you the IDFT. Okay, so where W star conjugate, it is equal to W of minus of Kn by n. Okay, so just nothing but you are multiplying it with minus Ca. Okay. So again, when you do this operation DFT, you will be getting the signal in this way: xk equals to x0, x1, and so on. And ultimately, you will have to report it as x of k equals to x0, capital X1, and so on. Okay. So if you look into the total factor, so as I told you, the modulus is 1 and the phase of that one would be minus of 2 pi by capital N. So what does this say? So the total factor values, it lies on the unit circle in the complex plane from 0 to 2 pi angle, and it gets repeated for every cycle. Because when you are on a circle, so what happens? 0 and 360 both are same. Again after 360, when you repeat, so it will be superimposing on a particular value again. Okay, so this is what it has been said, that after the 2 pi angle, the values, it starts to get repeated itself. Okay, and herein I have given you some notes. So this notes will be useful for you while you want to prepare for the examinations. Okay, so in the context of the DFT, the total factor represents the complex exponential term that modulates its sample of the input signal to compute its contribution to a specific frequency component. Okay, what it is saying, so you are basically multiplying xn with the wn, so all of the signal components, they are somehow getting multiplied with some of the frequency components. When you are in the complex plane, what is that? It is nothing but some frequency component. So okay, it is associated with some frequency component. So all the uh, signal components, they are getting multiplied to specific frequency components, and accordingly you are able to find out the frequency response of the signal. Okay, now in simpler terms, it is the phase shift applied to each signal, each sample as part of the DFT calculation, and this is the equation what we have discussed a few months back. So the next one, it talks about the FFT. So we will talk about FFT a bit later. So what are the properties of the twiddle factor? So the periodicity, as I already told you just now, why this periodicity is coming. You are going on a circular point, and after every 2 pi, when you will again move forward, so you will be coming across the same points. So due to that, there would be the periodicity. Okay, then symmetry. So the values of twiddle factors, they will be symmetric in nature. Okay, then magnitude of the twiddle factor. So magnitude, just now I told you, so magnitude, it would be cos theta square plus sin theta square under root of that one, and it gives you 1. Now coming to the periodicity value property. So the periodicity property states that the twiddle factor repeats itself after every n steps, that is the length of the signal in the index k. Mathematically, it is represented by this form: w k plus n, then n, which is equal to w kn. Okay, this means that if we add n to the index k, the twiddle factor does not change. It returns to the same value as it was for the index k. Okay, so why does this happen? It has been given over here. See, k plus n, so it is e to the power minus j 2 pi k plus n by n. If you break this down over here, then again if you look over here, so, and this is e to the power minus j 2 pi. So after every 2 pi, so if you see, since e to the power j 2 pi 1 is equal to 1, because a rotation of 2 pi radians or 360 degree around the unit circle returns to the same point. Hence w k plus n is equal to w k n. Okay, this shows that adding n to the index k results in the same twiddle factor as the original kn. Okay, what is the implication? If you are talking about a 4-point DFT, the W04, it would be equal to W44. Okay, so 0 plus 4, it will be 4. Okay, so W0, it will be equal to W4. Similarly, W1, it will be equal to W1 plus 4, it would be 5. Similarly, 2 plus 4, so W2, it would be equal to W6. Okay, so you look into this fraction Wk plus capital N, it is equal to Wkn. Okay, I hope everyone is along with me. Anyone? Your face looks quite fade. Yeah. Okay. Now coming to the physical significance. So if you look over here, what we are having? We are having a complex plane, real sigma and imaginary j. Okay. So we talked about that there is a circle. So this circle we are having, and its modulus is, that means the radius is 1. Okay, so we start with 0 and come to 2 pi. But if you remember, when we are discussing about Wn, what is happening? We are having e to the power minus j 2 pi by n. So under normal circumstances, if we want to calculate the angles, we go in the anti-clockwise manner. However, yeah, I am coming to that. So under normal circumstances, we will go anti-clockwise to get to the specific angle. However, since we are having this negative sign, we have to follow the path of clockwise direction to obtain the Tudor factor values. Okay. Now, coming to the calculation of the Tudor factor value. So W2, so here the length of the signal is 2. Okay. So how do we calculate this one? The thing is that total 360 degree we are having divided by 2 is 180 degree. So the first point it will be 0 and the second point it would be 180 degree apart. So it would be here, right? So here we are having 1 and here we are having at pi we are having -1. Okay. So now if you see 0 1 0 1, so 0 0 0 0 1 0 0 1 0 0 1 1 1. So this is 1, this is 1, this is 1, and this is 1 2, 1 2 is -1. Okay. So if I have to tell you what would be the next say W22, W22, W02 plus 2, what it would be? W2 2, which is nothing but W0. 0 2, n is here, so we can just negate that thing. So W0. So W0, with that we added capital N, we got W2. So W02 it will be equal to W2. Okay, done. Now coming to the 4-point DFT, 4-point DFT 360 कितना? True. So we will be putting 0. Here there will be 1 point. Here there will be 1 point. Here there will be all equally spaced 90 degree apart. Okay. So this is 1 minus j minus 1 plus j. Okay. So you calculate this one 0 0 0 0 0 0 1 2 3. So I have written the capital N over here, so I am not writing it within the matrix for my convenience, but whenever you are doing it, you please write those values. Okay. So likewise you get W1 W2 W3 W2 W4 W6 W3 W6 W9. Okay. Now 0 1, so all of this, see, these are 1. Okay. Next one is W1. W1 is minus j. Then W2 minus 1. Then W3 j. Okay. So W0. Then W2 is minus 1. Then 1. Then minus 1. Then j minus 1 minus j. So what we are doing? Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. So W159, they will be having same values. W048 they will be having equal values. W37 they will be having same values. W26 they will be having same values. You're getting my point? Here also, if you see, it has been written 159. So in that way, you already got the values. Now you just have to put it over here. Now clockwise rotation in the complex plane. So why clockwise? I've already told you, because of this negative exponent, you have to have the thing. So what if we try to use the anti-clockwise direction? So if you look into the values, these are conjugate to each other. Okay. Similarly, if you go at a later stage for a higher order, uh, this total factor values, we will see the values are already conjugated. So during the anti-clockwise direction, we will find we will be getting the total factor values that are suitable for inverse discrete transform, uh, in, inverse discrete Fourier transform. Okay, done, clear? So nk value for n equals to capital N equals to 6. If you see, so 360 by 6, 60 degree. Now if you see this minus j plus j, they are not coming into picture over here at all. Okay, so we are having 0, 60 degree. Then over here, uh, from here if you see another point, then again pi, then here, here. Now if you look into the values, these are conjugate to each other. Okay, these two values, they are conjugate to each other. Okay, so if you look into the coefficients they remain the same. So the coefficients they are the same. Okay, so the real part and the imaginary part, if you see, they would be the same, except this 0 and 1. Okay, except this at 0 value and pi value. Okay, so mhm. 60-degree angle, how do you calculate this? In class 8 9 here, this is 60 degree, this is having a radius of 1, this is having a radius of 1, this is 60 degree. Calculate the coordinate. Huh? Huh, 0.5 minus of j 0.866. So it's all about your trigonometric functions. So this is radius, this is, if it is 60, what it would be? Or you can also find out this one, the perpendicular one. So what it would be? Sine cos tan. है ना? So this is the your angle is given 60 degree. So you have the value of hypotenuse. You want to find out perpendicular, you apply sine. Okay. Similarly, the real component you find out. Okay. So by applying this, you will be able to calculate these values. And as I said to you, since these values they are conjugate to each other, few moments back I told you. So once you find out only one value, you will be able to calculate the other values just by looking into the, yeah. And I already told you that we will not be going beyond 8, right? So you just remember the values. Okay. So next, let us take a signal. The signal xn, it is given by 2 comma 0. So basically it would be xn equal to 2. It is a signal only with one value. At a particular instance, at 0th instance, we are having a value of 2, a value of 2, right? But the problem is that we just discussed that when we are dealing with DFT, we will not be able to deal with odd numbers. So we have to convert it to even number. So how do you do it? So at the second time instance, we put a value of 0. So this is called zero padding. This is called zero padding. So the logic is like that. At only 0th instance, if you are having 2, first instance you will be having no value. Third instance you will be having no value. Fourth instance you will be having no value. So we can easily write it as xn equals to 2 comma 0. The signal remains the same. You're getting my point? So we do that. Then we perform the 2-point DFT. We use the Tudel factor here. See, then this signal xn, it has been written 2 0 in the column wise manner. Signals are always given in row wise manner, but while computing the thing, we have to calculate it, we have to put it in the column wise manner. Okay, so this is 2 by 2 and 2 by 1. So we'll be getting row and column like this. That means 2 by 1 signal will be getting. You do the calculation. I hope all of you know how to do the matrix calculation. Again, class 10 11 year 10 11 12 yeah, subject. You find out the values, and this is your frequency component. Okay, so if I have to if I ask you plot this value, what you will be plotting? K, then at 0 you will be having this 2. You getting my point? Now we have got this value. Now we have to get back to the original signal xn 1 by 2 Tudel factor conjugate. There is no complex values, so Tudel factor remains the same. You do this. We have used this 2 2 as the what do you call, as the input. So it goes like this. You just do the calculations. You get the signal xn equals to 2 0. So in the first page, what you did, from the time domain we went to the frequency domain, and in the next step we again came back to the time domain. So these are two separate numericals. Okay, so it is up to you what you want to do. In many cases what we do is that we take the signal, we do go to the frequency domain, we do the analysis over there, and then we again apply the inverse Fourier transform. But we are not going into the analysis part. So uh, what you need to understand is that the analysis part, it will come bit later on. But from here I am just trying to I am trying to make you understand how the forward Fourier transform, forward discrete Fourier transform, and the IDFT, they work. Okay, now if we want to find out the inverse this DFT using the 4-point DFT, I have applied the same method. Now if you see, xk is 2 2 2 2 2. So if I have to plot it as a 4-point, it will be something like this. Okay. Now again using this value, I computed the xn. Are you getting my point? So again you see, we are going back to the original signal. Now what has happened over here? If you look into the frequency component, initially we are having only 2 2. Here we are having 2 2 2 2. 4 components are there. So you would say that, sir, everything is changing. Is it so? So if you change the signal length by padding 0, will it change the frequency response? The thing is that it does not change the frequency response. Okay, so what is happening over here? Take the case of a window. Say for example, we are having this in windows, right? So take only one row. I am able to see outside clearly the whole view. Now what happens if I close two of the windows with a black chart paper? So what will happen? You will only be able to see through the middle one, right? So does that mean that at the outside you are, there is nothing else? The scene is already there. The scene is already present. The only thing is that I have blocked the thing. That's why you are not able to see outside. Now, if I remove the center one and I center blockade and I put the blockade on the other layer, yeah, initially we block the other two. So now we block the center one and we open up the other two. So you will be able to see more view, but not the center one, right? So what is happening? Scene is there. Now, what is happening? As you are blocking the windows, you are not able to see the outer scenery. So that is not the problem of the scene. That is the problem how you are looking at the scene. Okay. Now, once you remove all the things, all the blockades, you will be able to see everything. Okay. Likewise, when we are doing the DFT, the frequency components, they are already there in the signal. You cannot add frequency components. You cannot modulate the frequency components. By doing the frequency, by adding the zero padding, by doing the zero padding, you are basically improving the resolution of the frequency component. That means how you are seeing the frequency component, okay, which are present outside this window. That is the main logic over here. So there is a very good example over here. We have taken xn equals to 2 2, okay. Now 2-point DFT, it is 40. 4-point DFT, when we went, see, this component is there, this component is there. So these two intermediate components, they were not there previously. Now as soon as we did the 4-point DFT, we got to see the additional two more components. Okay. In the next point, what is happening? It's very interesting over here. It gets interesting over here. If you see 4 and 0 are there, but not the other points. Now, why this is so? Why this is so? If you are not able to answer, that means whatever I have taught, you have not followed it properly. You're, no, my question is that, see, from x2 in x6, we are having only 2 points. However, these points have not been carried forward in 6 point. Other two important things are there now. We have not been able, we are not being able to see that. Now, why that is so? The answer lies in these charts. The positions, if you see, in the first case, in the first two cases, in the first cases, here and here we were present. In the second case, at these four locations. So in the first case, see, we are present here, we are present here. Similarly, we are present here, we are present here. Okay. Then here and here, it was the new addition. So along with the points which were there in the 2-point, we were able to see over here also. Now as soon as we go to the 6-point, see, we are present only here and here. Here and here we are not present at these two locations. So we are looking into the frequency components which are totally at separate positions. That's why when you come over here in x-axis, you have just been able to see only two positions which has carried forward from the x2 and not the intermediate thing. Now as soon as we go for the 8 point, right, those 4 points has been carried forward. What does this indicate? Again, whatever I told you, these frequency components are again already there, but we are not able to see those things. Yeah, and slowly when we are increasing the these points, this length of the signal by zero padding, we are basically opening up more and more points to look into the outer scenery. Okay, and that's why we are able to see a better picture. Okay. So key points about zero padding and DFT calculations. So frequency resolution improvement. Zero padding increases the length of the signal, which effectively increases the frequency resolution of the DFT. Why? Number of points are higher in the time domain. So in the frequency domain, your frequency resolution gets better and better. Okay. So this means XPK provides more finely spaced frequency components, but the underlying spectral content of the original signal does not change. Okay, that's what I showed you with that example. Okay, then original DFT coefficients in the zero padded DFT I already showed you, but it is just the explanation which have been given. No new frequency components. I already told you. Additionally, no frequency components will be added. Those frequency components are already there, whatever there in the signal, that will only be presented. Okay. So, periodic extension, the DFT assumes that the signal is periodic with a period equal to the signal length. When you zero pad, you are effectively increasing the period of the signal, which does not alter the existing periodic components, but rather makes the frequency sampling finer. Okay. So the original coefficients are thus embedded within the extended periodic representation, appearing exactly as they were in the shorter DFT. So frequency domain impact and interpolation. So frequency resolution, it gets increased. Interpolation in the context of zero padding. Interpolation means that the DFT after zero padding produces additional frequency components that fill in the gaps between the original frequency samples. These new points are not introducing new frequencies, but rather provide more detail about the frequency spectrum by smoothly connecting the points of the original DFT. Okay. Why interpolation occurs? It is the mathematical property. The DFT assumes the signal is periodic. Zero padding extends the length of this assumed period, resulting in more frequency points in the DFT. These additional points are mathematically interpolated based on the original points. And lastly, the smoothing. The interpolation smooths out the frequency spectrum, filling in the gaps between the original DFT coefficients with values that follow the general trend or curve established by the original coefficients. Okay. So the underlying thing is that we are not adding any additional coefficients. Okay. So coming to the DFT, again DFT calculation with signal length of n equals to 4. So the same method, just what I told you. Okay. So if I say xn equals to 111, perform 4-point DFT after zero padding, you have to do it, you get the xk. So then again, if I give you xn equal to cos pi n, so you have to get x of n, the values from there, perform 4-point DFT. So you have to find out 4 values and do the forward transform. and then again xk equals to 100 1010, perform 4-point IDFT. So in this way we have to do the IDFT. Okay. So before starting the next one, I would say that you practice these things. You still are left with 15 minutes. First you calculate the total factor values, at least 2 and 4 you calculate it. Don't look into this and try to concentrate